All right, as people are coming up to the stage, I see we have our first question here in the room. Go ahead.
All right. Good afternoon, everyone. My name is Sashank Wonga, University of Western Ontario. My question is to Zach. So the LiDAR scan you guys did at the field site, was it done using SLAM or non-SLAM methods using GPS?
It used a relative position of the rover. So we, this is back to 2024, so I had to think for a second. We didn't give the team GPS because we wanted it to be lunar analogous. But so essentially we knew the relative position of the rover. It would collect the point cloud, and then a team back in mission control would take each individual scan and stitch it together to create the full field topography.
Yeah. That's just what I wanted to know. Thanks.
Yeah.
Patrick Welly, NASA Goddard, Lise question. You asked for field guides. Do you have feelings about how old of a field guide you're willing to accept?
No, I think older ones is, geology probably hasn't changed much, so I'll take older ones.
Okay, great.
Cool.
I think I might have some Snake River Plain stuff.
Cool. Perfect.
Hey, I'm Jacob Richardson, NASA Goddard. I have a question for Alicia. I'm wondering if you can clear up a misconception for me. You said in your talk that that in this field site the craters are too dark, because with shadow cam we were seeing the craters actually can be a little brighter than we expected. I remember Robert Wagner saying they're as bright as this conference room, and I think it's probably the same lighting conditions. But is it fair to say that those sort of brighter, or brighter PSRs are lit because they have really large rims that are illuminated? Or do we also expect that these smaller craters at the tops of mountains that don't really have rim structures to reflect, are those also going to be brighter than we expect, or are those going to be similarly dark to your field analog?
That's a good question. Yeah. So I think the main source of the light in these craters is secondary illumination. So the light coming in from surrounding topography, bouncing off the topography and going into the craters. And also if you're looking at a larger crater, a larger portion of your view factor, if you're on the crater wall, is covered by your crater rather than the dark sky. So then you'll get more illumination on the inside of the crater. If your crater is deeper, for example. So I do think that maybe that will be a factor contributing to the brightness inside these craters.
Thanks. Can I ask a really quick follow-up? If the craters are, I don't know if this even is a good answer, but I'm interested in the answer. But if the light conditions outside the craters is actually really similar to the moon, which I think is really fascinating, and then the craters are darker than what we expect, then what's the answer for that? Why is that? Is that anorthosite for basalt, or is that something else?
You mean in the field site, right?
Yeah, the field site versus sort of, I guess, shadow cam expectations.
Yeah, so I've been thinking about that. So I wasn't sure if it might be because the albedo of the material in the field site might be different from the moon. It's less reflective, so you get less secondary illumination. But I looked it up, and they're pretty similar albedos, at least for where we were. And yeah, so I'm not sure. It could just be the brightness of the light is just not as powerful as the sun, wattage. And you have a lot more topography. Our field site was very flat. We didn't have any hills or anything that could reflect light into these craters. So that could be one consideration as well. But yeah, it's still a question that I don't have a good enough answer to. So more work needs to be done.
Thank you.
Hi, Carl Hibbets, APL. A question for both Zach and Caitlin. Very interesting talks on the future of how to explore the surface of the moon. A lot of what we hear from NASA, though, is about autonomy, pure autonomy, doing everything with the robots. Could y'all speak to the ability of robots, based off what you've seen here, robots being able to actually do what needs to be done? Because astronauts will not be there for but a few weeks at a time. And how could we get robots able to do it through maybe some model-mediated teleoperation or something like that?
Caitlin, if you want to take a stab, I'll defer to you and then I can answer.
Okay. Well, as far as decision making goes, absolutely, especially if you're deciding to go to a terrain that is not easily accessible, or maybe it would be better for robotics. But on a social aspect side of it is training those rovers as well, making sure that the rovers can be fully autonomous. A lot of testing certainly still needs to be done on that as well. And so it's decisions of not only how long does the rover need to go and the traverse planning with that though, but also trusting the data, right? And so that in itself can be like a whole separate philosophical level discussion of like human robotic trust, right? In that regard. So as far as decision making goes, absolutely. If the more that we hone in on how robotics work on an autonomous level, then we can really start iterating how to improve the system and how to improve our own training toward the robotics as well, because the robots are only as good as what we train them, right? All right, Zach, your turn.
I think to build on that, there's a couple different ways to answer it. One of the things we saw when we did our rover analog in this lunar south polar analog lighting was that the dynamic range of the cameras on the rover were not as good as the human eye. So you're running into navigational issues that humans in the field don't have. And just the mobility of a human with legs as opposed to a rover with wheels or treads. Humans can cross more terrain relatively quickly than a rover over a longer period of time. I guess an autonomous rover could, if it can survive the night, keep going. I think it really depends on the task you want to have completed. For something like taking a series of scans at regular intervals, that's probably something best left to a rover, a robotic system, that you're not burning through oxygen or valuable astronaut time to do that. But if you're trying to find the best sample that involves moving over, rough terrain and picking up and looking at rocks, that's still a very human thing to do.
No replacement for astronauts yet.
Not yet.
Thank you.
Yeah, Jorge Nunez, APL. First of all, great talks. I mean, love it. And sadly, you just can't ask everyone individual questions. So, but this one is kind of targeted for you, Zach, and Casey. So, I mean, very cool stuff that you guys are doing, and especially with like leveraging sort of LiDAR and hyperspectral imaging, right, which is really enabling, especially for astronauts. And so, but I'm curious as though, right, I mean, it seems like to get that kind of data ahead of time, right, you need to have some, like in your case, like, a rover or some kind of like spectroscopic imaging system that be able to collect that spectroscopic data ahead of time so that the astronauts have that information to then help inform the sampling strategy or where they're going to go, right? With the traverse planning and everything. And so I'm thinking in terms of just like, Artemis missions, right? Like Artemis 3, Artemis 4, right? They're probably not going to have some kind of rover, or do you think that they probably might need to have some kind of, maybe precursor rover or something like that to the landing site to help sort of do that initial reconnaissance and get sort of like the LiDAR data, spectroscopic data to help identify, okay, this is kind of like, where we're going to go, or how would we try to get those kinds of data sets ahead of time, especially when you don't have those kind of precursor missions.
I'll take a stab first. I think that, yeah, if you have a precursor mission that you're going to return to the same site, which is not a guarantee.
Right, like if you imagine like LTV.
Then you can leverage that asset for just an Artemis mission like Artemis 3. There are other ways to sort of tease this out. Whatever landing craft, the human landing system will have to come in and will have to sense a safe place to land. So that's likely using photogrammetry or LiDAR, at least of the immediate landing site, to land. So if that data becomes available to the science team, you could work in things like that. We've also done some testing with the Artemis 3 astronauts will have video recording from their suits. We're not sure when that video will be downlinked, probably along with the camera photos later on. But if it does get downlinked during the mission, you could run an EVA and then get those photos back, do photogrammetry from the video even, and then have a terrain model to use on subsequent EVA,
right,
even during the same.
Yeah. Yeah, I don't know if Casey, if you had any other.
Yeah, no, I was just going to say, for HSI, it's you can use orbital data to project what the mineralogy might be on the ground. The resolution is going to be really coarse. Absolutely, you might as well just use a map, right? But if you can put an HSI on the lander, and it can scan the area before they step out of the lander to do their EVAs. That would be something that could help. In terms of like long term, like a pressurized rover, if the pressurized rover has an HSI imager on top, one, it can help not only with the navigation of the rover, but it can scan the site before you get there. It can do all of the mapping so that the astronauts don't have to think about doing the mapping. And also it can make the traverse plans for the astronauts more efficient, because you already have an idea of the mineralogy that's there, the samples that you want to go investigate in person and see and possibly collect. And then you can also have, the before and after of the contamination that might be present.
Great. Thank you.
All right, I think we have time for one more quick question here in the room, and then we'll wrap up the session. Go ahead.
Great. Thank you very much. Outstanding session. Great way to wrap things up. I'd like to drill down a little more into the lighting analog at Cinder Lake. So in our Moontrack portal, when we do our ray traced lighting analysis, and as we try to move that to our Mars portal, we find that there's significant considerations that we have to make for atmospheric scattering. I'm wondering if in your analog that if you are taking any considerations into effect for atmospherics.
No, that's actually a really good point. No, I did not think about the atmospheric scattering. Yeah, so I will look into that. We did have some glow in the sky from downtown Flagstaff, so it was obvious that, there is like contamination from that. But yeah, atmospheric scattering is something to look into. So thank you for letting me know about that.
All right, thank you. With that, I think we can thank all of our speakers one more time.